Okay, so earlier this year, Google and Drew launched Password Alert, our plugin for Google Chrome. Very basic, simple idea, and I'm not going to steal this talk, but I can tell you this is one project I really worked with, and I didn't threaten to do that.
I don't remember that, but I might have forgotten.
Come here and do this specific talk because I think the ideas, concepts of this is really, really good. I love this, and I'm really happy to hit from Google.
Great, thank you. All right. So to start off, I'll be talking about Password Alert, which is sort of an anti-phishing tool. I'll give a quick overview of sort of password phishing, just so we don't leave anyone behind. Talk about how the tool works. Talk about some of the security challenges we've had with it, and then talk about some of the effects afterwards, sort of how it's been useful. So first, the sort of initial premise is that as sort of passwords and security people, we really make sort of these unreasonable demands on users. There's this complicated story, especially in enterprises, of where should you actually type your password? And that turns out to be a really complicated question, and we sort of expect users to actually know. You know, there's the obvious main login page, which is great, but what about some internal corporate Oracle server that verifies your password using LDAP after the user enters it? Like, is that okay or not? And that's a really good question. And similar with like third-party vendor sites, and to expect users to actually make these decisions every day when you're using it is not a great idea. Similarly, we're sort of expecting users in webmail and web-based authentication to understand the format of domain names, which is kind of complicated. You know, the top one to us, that's pretty obvious, that's the right one. And the second one is pretty obvious, it's the wrong one. But it's just subtle things that make it different. You know, dots instead of dashes, and the order of words and things like that. And it's really unreasonable to demand that users actually understand how a domain name is formatted, and to make that correct decision every single time. And then along with this, of where it's okay to type your password, is the concept of password reuse, that we expect users to have 50 different unique passwords, which doesn't scale unless you're using a password manager or something. So a quick overview of what password phishing is. You know, it's basically just anytime an attacker tricks a target into typing their password or giving it to them. And a simple example is, you know, an attacker emails a link, and the email might say, hey, you know, here's a Google Drive attachment I've shared with you. Click on this link in order to view it. User clicks on the link. It doesn't go to Google. Instead, it goes to evilsite.com, and it says, hey, give me your Google password, your Hotmail password, your Yahoo password, if you want to see this document. The user goes ahead and types in their password, and if the attacker has access to their data. It's a super simple attack. You know, you basically just go to a legitimate login page, file save as, modify the place it's posting the form, and then the attacker has access to it. This is super common. You know, all statistics are pretty much made up, but some large majority of account compromises are due to this pretty straightforward, simple phishing, nothing magical or really interesting. So how can we actually protect against password phishing? Initially, there's sort of this idea of, well, in addition to password, we should have some other factor, some two-step verification, like maybe it's an RSA secure ID, or maybe it's HOTP or TOTP from Google Authenticator, so that after you pick your password, it'll ask for this code. But of course, the attackers can just ask for that code as well, and then use it to authenticate. We see a lot of attackers do this, like Syrian Electronic Army and other people. Another idea that we have is with things like Google Safe Browsing, where we crawl a lot of the internet and then we analyze pages to see if it looks like a fake login page, and if so, Chrome or Firefox will display a big warning and say, hey, please don't go here. And this works great for sort of large-scale phishing sites that are sent to thousands of people. It also works great if you're protecting like the Google login page or major banks' websites. It doesn't work as well for, say, your company's own login page that looks different, or sort of targeted sites that maybe Google hasn't crawled that are sent out to like, you know, tens of people. So the real solution to all this password phishing is to have this, hardware crypto authentication. Last year, released something like Security Key. And there's similar sort of smart card solutions that have been on the market for a long time. And essentially, this is just a hardware device that you put in the USB slot, and it does the authentication with the server. It verifies the server is who it says it is. It only attests to the proper servers that you are who you say you are. And this way, you take that credential out of the user's hands and only give it to the proper server. This requires some hardware and things like that. And so about 4 or 5 years ago, we were sort of in between these two stages. We had two-step verification with OTPs that people had to enter, but we did not yet have this hardware crypto authentication security key-based thing. So I created a tool to sort of bridge the gap between the two before we had security keys rolled out to everyone. And so the idea with Password Alert is it relies on the core effective phishing that a target becomes a victim when they type their password into the wrong website. When they get that phishing website, they put their password in and they don't realize it's not the real login page. So similar to a spell checker, password will detect whenever the user types their password. And whenever it detects the defective password, it checks the URL and says, hey, is this actually the legitimate website or not? And if it's the wrong place, then it goes out and takes action. So sort of a quick overview of sort of the workflow here is Password Alert is a form extension that sits there and learns about your password whenever you successfully authenticate to Google. Then once it learns about it, it saves a reduced bit salted hash in Chrome's local storage. And from then on, it can compare whatever you're typing to see if the most recent keystrokes hash to the value that it has saved. And if it does, then it knows that you typed your password. And then it can trigger an alert. So if you're a consumer, normal user using Gmail or something, then it could display an alert similar to this. It says, hey, you just typed your Gmail password on a non-Google login page. Maybe you want to go ahead and change your password before the attacker has a chance to use it. Maybe you want to ignore it because you're okay sharing passwords with Facebook or some other major site that you expect to secure. And so one thing you might notice is that it's now doing hash every time you type anytime you type a keystroke, anytime you press a button on your keyboard. And so this might seem sort of computationally intensive. About a year ago, the idea that we were using Password Alert internally at Google leaked on Hacker News, where someone posted and said, oh, my friend at Google, they have this thing and it detects if you type your password in the wrong place, and they're stringent about the passwords. And the first response is, oh, that seems really unlikely. How would you even do that? That has to be way computationally too intensive to actually compute hashes on all the text in Google documents or something like that. And it turns out, luckily, it's not too CPU intensive. Doing the hash takes way less than 1 millisecond, maybe like a tenth or a hundredth of a millisecond, and we haven't seen any sort of noticeable slowdown in behavior even on slow, old Chromebooks and laptops and things like that. So one advantage of this over things like security key that makes it easy to deploy is you don't actually need hardware that you have to give out to people. You don't actually have to sort of train or educate your users about what's going on. You don't have to say, oh, every time you log in, press this different button. Instead, it just detects when something wrong happens. Then when something wrong happens, then it goes ahead and lets the user know, it lets your security team know, that sort of thing. So I'll talk a little bit about the enterprise use case where we have both the Chrome extension and also a server-side component. So the Chrome extension we're talking about that I was describing the workflow before, you can configure it in the enterprise setting to also protect your corporate SSO page, like your company's login page. It also has, that way you can learn about the password to protect your corporate SSO password. And it also has some basic HTML checking where it tries to detect in advance that it might be a fake login page, which is sort of a side feature of it. In addition, you can figure where to send alerts to, and these alerts would have things like, oh, this user typed their password in evilsite.com. Maybe you want to take action. And you can configure this using Chrome App Management to push it out to people in the Google for Work domain, and you can use existing configuration things for your operating systems, like Windows Group Policy and that sort of thing. And so the enterprise server is what receives alerts from the Chrome extensions. And so we've released an open source App Engine app. So you would take the source code, upload it, run it yourself in App Engine. We're also working on a Google hosted solution where you don't have to manage the App Engine app. You just log into a web app like you would expect it to. So if you're interested in that sort of thing, go ahead and email me and we can add you to the trusted tester so you can play around with it without having to run your own App Engine app. And similarly, you can actually have it report to sort of whatever setting you want. It just does an HTTP post. So you could take action or log it however you want. And so the server has some basic features of if it notices the user types their password in the wrong spot, it can expire the user's password to force them to change it right away. You can email an alert to the user and or the security team to let them know what's going on. And the admins can also view what alerts have triggered and then also categorize domains. So you might say, yeah, that internal corporate Oracle financial server, that's okay to reuse their password, so we don't actually want to take any action when the user types their password there. So that's sort of the story of how it works and the basics behind it. So if anyone has any questions about it, feel free to interrupt or anything. And then I'll talk a little bit about sort of the ways that we make it safe so that it doesn't actually make the user any less secure, and some things about evasion results as well. Cool. So the first sort of tenet is that the password data is only kept locally. You take a SHA-1, per machine salted, only store 37 bits of the SHA-1 hash. And this hash is never sent anywhere. In the enterprise case, we sometimes send reports about misuse of it, but it only includes like the username and the URL they use it on, but it does not include any of the hash data or anything like that. And in the non-enterprise case, the normal consumer use case, we just install it for your Gmail account. No data is ever sent from your machine about what websites you type it on or anything like that. And this password hash is stored in Chrome's local storage. The local storage in Chrome is isolated for origin, so other extensions cannot see the hash, other web pages cannot see the hash, they have separate origins. And this is sort of a similar protection to what you might expect to have with your authentication cookies that you already use to authenticate to web services. And so speaking of isolation, Chrome extensions have this nice isolated world policy, where content scripts that are running don't run in the same origin. They sort of run in the same origin as the web page they're being injected onto, but it's a little bit special. And so this isolated world concept allows the content script, in this case password alert, to inspect in and get data from the web page that you're visiting. So it can do things like get keyboard events, it can see what the HTML looks like. However, the opposite is not true. That web page you're going to does not have any access to the Chrome extensions, password alerts, say hash or JavaScript that is running, things like that. So this is a big security boundary that we rely upon. So the password alert can do all this interesting work with the malicious web page without sort of exposing anything to the malicious web page. And so you might be thinking, well, sure, you're exposing something in that you're accepting keystrokes, keyboard events from the malicious web page. So one attack scenario is I'm running a malicious website. I'm going to go ahead and generate a lot of fake keyboard events. And I'm going to see if this password alert warning shows up, or if I lose focus, or if something like that happens. So the malicious web page is going to generate thousands of keyboard events trying to basically brute force the password. So we deal with this and protect against it in a few different ways. So the first sort of main defense is we discard keyboard events that look like they're programmatically generated. In Chrome, there's no sort of surefire way to do this, but thankfully, programmatically generated keyboard events tend to have a few different things set, like they don't have the window view set properly to the window. They don't have the character code set, depending on how you do it. And similarly, if you try to replay legitimate keyboard events, the timestamp is not able to be changed. So we also throw away timestamps that are not monotonically increasing. So this is sort of a fragile protection that's pretty core to it. So a colleague implemented this is trusted idea, which is something that Firefox supports. And if a keyboard event has the is trusted set to true, then you know it came from an actual keyboard and it was not programmatically generated by JavaScript on the malicious website. And so this feature is in Chrome Canary, so you can go check it out and play around with it for other things as well. It's implemented slightly differently than Firefox. In Firefox, is trusted is exposed to even the DOM of normal web pages that you visit. And this sort of isn't a real security feature because other things on that web page can also modify the is trusted value. So in Chrome, is trusted is only set for Chrome extensions because they're in the isolated world, so we can pass the special value off to them that cannot be modified by the malicious content on the page. So we wanted to make that so that developers not sort of make a mistake there. Another layer of defense that we have as well is that we rate limit the keystroke checking so that we limit it to about what a normal user might be typing. So in this brute force scenario, you might be sending thousands of keyboard events, and once we notice that you're typing, checking way more than what a user can type, then we just start dropping the keyboard events and checking for it. And then another thing that we have is this idea of the reduced bit hash that I talked about. So you might be wondering why earlier we only saved 37 bits of a hash. And so the idea here is that we're intentionally introducing collisions. So that if you find a way to brute force the password either through the generated keyboard events or by, say, stealing the hash off your local file system, which you're in trouble if the attacker can do that because they could probably just steal your cookies anyways or log in as you or steal your sensitive data and rifle through it. So we intentionally introduce collisions. So if they're brute forcing it, they're going to likely find a lot of other passwords that also hash to the same value. And of course, this is really dependent upon your password entropy. If you have more than 37 bits of password entropy, you're going to expect other passwords to also hash to the same value. So if you have a 10-character randomly generated password, then yeah, you're going to have thousands upon thousands of other passwords that hash to it. And the attacker is not going to be able to discern which one is actually your password and which one's not. And they'll have to go through and trial of them, say the web interface, which will be rate limited server side. However, if your password is 1, 2, 3, 4, 5, 6, then sure, they're going to know that that's your password and they're going to notice the collision right away and tell what it is. And so this is sort of a balancing act. If we store too many bits, then there are not enough collisions. If we store too few bits, then there are a lot of false positives. Meaning if you're typing normal things that are not your password, one of them could happen to hash to what it thinks is your password. So we settled on 37 bits, which equates to about one false positive for 20,000 people typing for a year. This is a very sort of rough math because people don't actually type randomly. And I'm sure they have all sorts of patterns and probably entire PhD dissertations about it. but it sort of worked in practice, and it was a rough number to tell whether you should say 37 or 60 or 4 bits, things like that. And so all those ideas and attacks I was talking about before are attacks that would reduce the security of the user who's actually using it. So if these attacks worked, then you'd be sort of worse off for having the extension installed. So what I'm going to talk about now are sort of evasion techniques, which are ways that the malicious web page could evade detection by the tool. Similar to like an intrusion detection system or an antivirus thing, ways that the malware could avoid detection, but you're still sort of no worse off. And this is sort of a category that we expect to be a cat and mouse game, where you'll come up with some new evasion technique and then try to fix it. And similarly, we'll still detect existing phishing web pages that don't use any of these techniques. And I guess it's worth noting we haven't seen any of these techniques in the wild. And I've been looking as part of my day job, where we do sort of threat intelligence type stuff. So one evasion technique is that, say, every time that you type a key press on the web page, go and open a new tab and switch to that new tab. And this exploited the fact that we were saving the keystroke buffer per tab. And so if there's a new tab, all of a sudden there's a new keystroke buffer of these keystrokes. So we fixed this by, instead of doing it per tab, doing it per browser. In that way, users only typing in one browser at a time, so it seems to work pretty well. Similarly, initially we displayed the warning banner in the actual page, in the DOM, because it was nice for the user. You don't get a new tab or something, you display it, they see what URL they're on, things like that. But of course, the malicious page would just then hide the DOM there. So we switched instead, opening up the warning in a new tab. And so this new tab has a separate origin of the malicious page, and therefore doesn't have any access to the tab itself. And there's a bug right now where native URIs in Chrome, Chromium don't actually get content scripts injected into them, but that's something that we're looking at fixing. And then there's this sort of broad idea of evasion, where whoever gets to act first sort of has control over the event. So if the malicious page can get the event before we can, the malicious page can do things like prevent default or stop immediate propagation to prevent that keyboard event from bubbling up the event chain. And so in order to deal with this, we changed our run ad to be running at document start. So that way the content script actually runs before the malicious page is even loaded. So the malicious page has not had a chance to actually set up a keyboard event listener. A sort of more tricky one was that when you press a key on the keyboard, it generates a key down event. When you sort of press the button down, and when you release it, it generates a key press event, which is sort of the calculated thing that's actually been typed. So one interesting evasion technique here is that whenever the malicious page would see the key down event, then it would go ahead and refresh the page so the key press event never actually triggers. Because now all of a sudden it's a new view, a new page, things like that. So we had to switch to monitoring both key down and key press. So that seems simple. But the trick there is that key down does not actually expose the character that was typed. Instead it exposes something called the character code, which is more like a lower level abstraction of the keys in the keyboard. Maybe like L is column 12, row 2. So it gives you this number, and that number sort of translates into a key, but not really. It doesn't take into account internationalization, like different keyboard layouts. It doesn't take into account caps lock state or shift state. So we had to write a library that would sort of guess what it thought was the shift state, and track what caps lock was on or off, and things like that. So it gets pretty complicated. We at least have sort of a rough cut of that. It seems to work most of the time. So that's sort of the list of attacks and evasions the ideas there. And so then the main question is sort of all of this worth it? Does it actually work? So we've been using it for 3-something years, probably 4 or 5 years at Google internally on all of our computers. And so we've seen some significant things. So we've had a big change in user behavior. We've had an 87% reduction in corporate password reuse. And by that I mean people that would use their corporate password on other websites like LinkedIn or some vendor website, things like that. And so when they reuse their password, then you notice it and say, hey, change your password. Here's an email to explain exactly what happened. We've also seen a 70% reduction in accidental typing. And by this, I mean when a user types their password in to the wrong website, even though that's not the correct password. Maybe they're not sure what their password is for this expense reporting system. So they go ahead and try their corporate password because why not? It's a company's sort of website. And similarly, one of the other things I do at work is help manage these internal penetration testing tests. And it was one of the things that sort of initially spurred me into working on this and making it, is that we saw password phishing was a useful attack that was super simple and worked in the real world. And so with Password Alert, we were able to catch something like 70% of internal phishing tests. That number is basically made up because, of course, the phishing depends heavily on how you do it. If you're targeting Android users versus desktop things, you're targeting places where Password Alert is not running, like iOS devices or Android, then of course it's not going to detect it. But we still saw it catch a lot of them. It stopped a significant attempted attack of Google with Password Alert and with other detection and monitoring systems. And also some great analysts were able to stop an attack when it was still an attempted attack before it became an incident. So that was a big win that made everyone's lives easier. And we've also had people that have left Google and gone and implemented it off at other companies as well for their own corporate infrastructure, which is one thing that helped us push the idea of releasing it for free and open sourcing it, sort of letting everyone use it. So if you want to try it out, there's a link there. We have it's all open source on GitHub as well, so you can go check out the code. We're happy to take contributions. One of the earlier speakers, Scoobs, has contributed to it as well, so really grateful for his contributions, and of course for any contributions that anyone else wants to make as well. So does anyone have any questions or anything they're wondering about? So the question is, how does it work with password managers? So in general, it doesn't really. So they don't sort of conflict. But the nice thing is with the password manager is that it makes the decision for you. So the password manager is only going to put your password in when it's actually the real website. So that's sort of another nice way of taking the decision out of the user's hands for where to type their password.
Since you're using is trusted, how does this work with VPN software or remote desktops, for example?
I don't think it should really be is trusted. So I think that's still per browser. So it's still coming from the page that you're going onto, and the content script is being loaded directly into that page. So I think regardless of everything, I think it should still work. In the is trusted, we're not actually using it yet because it's still in Chrome Canary. But once Chrome Canary goes to stable, then we'll start using it.
In the case of the password managers, where you said it doesn't work with them now, but also have the GitHub and GitHub, is there any reason you couldn't integrate it in a way that, say, it would work not just on one password, but anything in your vault, regardless of where it is? So if it detects on a web page like, oh, this password is elsewhere in your vault, that's, and sure, maybe you should do something about that.
Yeah, definitely. That would be a great feature. The one thing I think would be difficult is having the extension get access to the passwords in your vault. If you're using something like the Chrome Password Manager, I do not think it has access to it. And I think in cases like LastPass, it's also running as an extension. It stores the data in the extension. So the extension would not have access to it unless they implemented some sort of API that allowed this particular extension to get access to it. But I could be wrong. I'm not actually sure.
That also would not be very easy to do in one password, simply because, again, the browser extension doesn't have access to
More questions?
So for the truncated hashes, which is 37 bits, and I think there could definitely be an argument for more or fewer.
Mm-hmm.
Have you actually done any sort of empirical analysis where you brute forced your truncated hashes to find what the collisions look like, and then figure out, maybe a human being look through, say, 200 collisions before it's too many? Can you pick out the real password out of 200 collisions, or 300 collisions, or 50 collisions? Like, have you actually done any sort of real analysis here to figure out 37 bits is the right choice, or maybe 40 or 32 or whatnot?
Right. So empirical and real analysis might be a strong phrase. We've done some sort of anecdotal testing of that. But sort of the reason we didn't go further is it really depends on the strength of your password. So some people, like security team type people, choose really random passwords that are hard to distinguish, that are long. And with the 12-character password, you all of a sudden get so many collisions it's infeasible for a human to look at it. And you can do other analysis. And a lot of people choose really poor passwords, as I'm sure everyone knows here. And those are really easy to spot. So yeah, the number 37 is very sort of fuzzy. At 36 or 38 or 40 would totally be fine as well. We had to choose some number in that range.
Hold on.
Would there be any reason why you couldn't set that as a user assignable one? Like maybe 37 is the default, but if they really like it for some specific unknown reason, they could set it higher or lower, or would that really clash with the image of it?
Yeah, in general, that should be fine. Basically, right now it has 0 settings for the consumer side. So I try to go with that approach of it not actually requiring any configuration. You just install it and it just works without the user having to do anything. So you certainly could, and the source code is there to change it. So if someone did have a strong reason, it'd be fine to change as well. Yeah.
So there might be something that you built into it that allows for, if it's the first 37 bits and we're ignoring rapid keystrokes, wouldn't it be possible to inject a series of rapid keystrokes and make it ignore the user's input?
Sure, but that would still require you to have some way to inject keystrokes, which with the is-trust would be sort of a hard security boundary, and now we have this sort of softer security boundary where it's not possible to inject keystrokes. But certainly if you found a way to inject keystrokes, you could hit that rate limit, and then it would ignore it. If you had a way around the first sort of protection there, certainly.
Do you get any complaints from users that they say this alerts every time they try to type the name of their dog?
Gotcha!
So in fact, every email that got sent out, lots and lots of them, when people respond, I reply to them as well. So it has provided really interesting insight into users and what they think domain names are and what they're using their passwords. And there was at least one case where the user said, oh, I was typing X, where X is some field that you would fill out normally, and it alerted. And they said, well, because that's my password. And it's just an example of the user chosen something sort of equally poor to their dog's name as their password, and when it types, it alerted. Yeah, but in general, those complaints are sort of good, and it provides an opportunity to educate the user about, if your password is just, if you're randomly typing it into email documents or whatever, you probably want to get a better password. And similarly, whenever they say like, oh, I really thought this was a Google login page, there was a big Google logo at the top. Then we have a chance to educate them about, well, look at the URL and actually maybe check the URL when you're typing it in, because that's sort of what we care about. But when they type it in some third-party website, they say, well, it was required for work, so use my password. It presents a nice opportunity to send them an email and say, well, we still don't want you using your password there. So yeah, I've heard all sorts of things from users, all sorts of angry responses about what they were doing, but in general, it seems to work.
But perhaps a silly question from me, but I'm very interested. There's lots of research showing that people do not change default settings in most software. That also basically means that in many cases people don't want to install plugins. They don't know about it. What would be the benefits and what would essentially be eventually the drawbacks of implementing this directly?
Yes, that's a great question. It's something we've been talking with the Chrome team about. And sort of one of the advantages we have now is when a user does intentionally install it, they sort of know what they're getting into. They sort of expect that when they reuse their password somewhere that they're going to get a warning. And if it's directly built into Chrome by default, users would be pretty surprised. And in fact, our initial sort of direction was to go and prevent anyone from typing their Gmail password into any other website. And of course, all the people that actually have users and talk with users said, well, that's totally infeasible. Everyone will stop using it. And it turns out that's pretty much true. Which is why we've sort of leaned towards this sort of corporate use case as well internally. But so you could have some sort of optimal, and that might have a slightly lower friction than installing an extension, where the extension says, oh, it's going to have access to all of your web page events and things like that. If it's just an option someone will check, it would be easier to sort of get around the evasion things. And we're talking with the Chrome team, and it turns out sort of it's easy to write a Chrome extension. It's much harder to sort of change the UI in Chrome and change the password manager and that sort of thing as well. It takes a lot more work.
Okay, that's very cool.
So this is sort of a non-cryptic question, which is unusual for me, but the average user has no understanding of one-way functions, no understanding of hashing, no understanding of hash collisions, truncated hashes, anything about that. So if you wanted to implement this sort of globally, you'd have to avoid the issue of, oh my God, Google is watching everything that I type, which is sort of true, but requires some special marketing to describe how this works to a user so that they understand why it's safe, even though everyone in this room already understands why it's safe. So have you guys thought about that? Have you guys figured out how you're going to market it, or how you're going to describe it to average users if you want to do a worldwide deployment?
Sure. So somewhat surprisingly, that hasn't really been a concern. Users have not sort of complained about the idea of sort of watching what they're doing or anything like that. And I think a lot of that is attributed to being users intentionally installing and inspecting this behavior. And so people seem to either not understand or not care about it, and so that it hasn't really been a concern. Internally, when we deployed it in the corporate, there were a lot of discussions around privacy and people not necessarily knowing what it does. But I think that was a big difference because it was pushed out to employees automatically, and they didn't sort of opt into it, and they didn't sort of choose to do it. So there were definitely more discussions there internally.
Okay, well, thank you, Drew, for coming to
Yeah.